Okay, so thanks to the organizers for this opportunity. So I will be talking about harnessing information from higher order statistics in cosmology. This has been touched on by quite a few speakers this morning. So I will present my own version called the K nearest neighbor distributions. This is work done in collaboration with a whole bunch of collaborators. So let's get started. So we are living through an era of rich cosmological data. Now that data can look like continuous maps. So maybe the Planck temperature field, weak lensing mass maps, or they can look like discrete objects. So these are the DESI galaxy, these are galaxies in DES. So this data comes in various formats, okay? And then following on from the last talk, this is the posterior from the BBH mergers in LIGO. So data can look like this as well. Now, what we want to do is we want to use this data to answer some of the fundamental questions in cosmology. So pick your favorite. Is it early universe, inflation? Is it late time expansion? Is it neutrino mass? Is it dark energy? So we want to answer each of these questions. And to do that, we need to be able to extract the most information that we can from the data. Now, over the last few years, we are getting better and better at predicting the gravitational collapse of a lambda CDM universe. Okay? So this is a simulation thanks to my student Vikhyat. So this is just looking at the density field evolution as a function of the neutrino mass. So this neutrino mass again is one of the things we have promised the community that we will deliver on. So we know how to run simulations deep into the nonlinear regime as a function of these quantities. But most of the analysis still uses the 2-point correlation function. So our favorite DAO peak, for example, is measured in the 2-point correlation function. Now the 2-point correlation function is the ultimate summary statistic for a Gaussian random field. So for the Planck map or for very large scales even at low redshifts, the field is a Gaussian random field, and so the 2-point correlation function is enough for us to get the total information out of it. But as we saw from the previous simulation, on small scales the field is extremely non-Gaussian and the power spectrum is not able to extract all the information there is. And ironically, cosmological surveys will provide exquisite data precisely in this regime. Okay? There is low sample variance on small scales, so that noise is low. And we will fail to fully utilize the power of these experiments if we do not look for techniques that can probe the non-Gaussian information. Okay? I'm not the first person to talk about this. This is an active area of research. You can broadly split it into two sort of techniques. One is called field level methods. I don't know if anyone is going to talk about it here. The other is through human interpretable higher order statistics. We've already heard in the morning about the bispectrum. We've also heard about the 1-point PDF. There are Minkowski functionals. We heard about the Mach power spectrum and so on. So this is a very active area of research. What I'm going to do is first give you a list of what we want from summary statistics that are looking to go beyond the Gaussian part. First, of course, they should capture as much information about the data distribution as possible. Secondly, it should be easy to apply to different kinds of data sets. You should be able to talk about autocorrelations in a data set, cross correlations between data sets. You should be able to apply it to continuous maps, discrete data sets, everything. Third one is that they should be computable in feasible time on the data and many instances of theoretical predictions, because for really nonlinear scales you can't get away from simulations, so this has to be quick to compute. We also probably want to understand the underlying theoretical connections between the various proposed summary statistics. This will help us understand which summary statistic is better at doing what, how to break parameter degeneracies, and also how to mitigate the effects of systematics and potential errors. Okay? With that, let me dive into a particular summary statistic that I have been developing over the last few years. This is called the K nearest neighbor distribution. So let me give you an illustration of how it works. So suppose my data lives in this square, okay? First what I will do is I will sample this with a dense set of query points. So these lightly colored points I'm going to call query points. The actual data points are these more solid points, okay? What we do is, given this data, we go to every query point and ask how far away is my nearest neighbor data point, okay? I can go to any query point and ask this question, how far is my first nearest neighbor, second nearest neighbor data, third nearest neighbor data, and so on. So at every point, I will generate a list of k distances. I'll visit another query point and generate this list again. Now, let's say we look only at the nearest neighbor points from every query point. I can sort the distances, and that immediately gives me the cumulative distribution function of the nearest neighbor distances. So a single measurement is sufficient for a range of scale. So if I plot the CDF, I get the CDF as a function of scale. So this is the cumulative distribution function of the nearest neighbor data points, the second nearest neighbor data points, the third nearest neighbor data points, and so on. And the second thing, very crucially, is that this is extremely computationally inexpensive. This scales like n log n, so just like the 2-point correlation function. So this is super fast. This works on a few seconds on a single core. So this is what I am calling my summary statistics, the k nearest neighbor cumulative distribution function. Okay? Let me quickly give you a flavor of what it is measuring. So on the left and the right, I have equal numbers of points. On the right, I have just thrown the points randomly over this volume. On the left, they are actually gravitationally clustered. What is the first thing that strikes you between the two? I would say the first thing that strikes you are these empty regions, which are the voids. So if a data set is clustered, compared to another data set with equal number of points but with the same number density, you will see larger gaps. So if I am a query point sitting here, my nearest neighbor data point is going to be far away. So my cumulative distribution function plateaus to 1 at a larger radius, okay? So more the clustering, the CDF value changes differently, okay? Okay, of course this is not quantitative. Quantitatively, we were able to write down the generating function for those k nearest neighbor distributions. So each nearest neighbor distribution is just a derivative of this generating function. The nice thing about the generating function is that it has a closed form expression in terms of these quantities I call xi of k. Now, these xi of k's actually correspond to integrals. So let me look at the k equal to 2 piece. The k equal to 2 piece is an integral of the 2-point function over all configurations that fit into a sphere of radius r, okay? So this is one configuration that fits here, this is another configuration that fits there. So I can write the integral over all such configurations, and that is one of the terms here. The next term asks me to consider triangles instead of just pairs of points. I integrate over all such configurations, so this is actually an integral over the 3-point function. In this way, you can show that the generating function and therefore the CDFs are actually sensitive to all endpoint functions in the data, okay? And we were able to show in a number of cases, both on data and on simulations, that we get much more signal to noise compared to the 2-point function because we are sensitive to all endpoint functions in the data. So this is one paper on actual data, which is the 1000 richest red mapper clusters in SDSS. But for example, in this study, using simulations, we were able to show that if you are interested in primordial non-Gaussianity, the fact that these nearest neighbor distributions are sensitive to all endpoint functions in the data helps you break degeneracies much better between primordial non-Gaussianity and halo parameters compared to even combining the power spectrum with the bispectrum. Okay, so 2 plus 3 point is still not as good as the KNN distributions. I want to spend a little time on this relatively new paper. So we have understood the k nearest neighbor distribution functions from the algebraic perspective of how they connect to the endpoint functions. In this paper led by my student Kwanit, we looked at the geometric interpretations of these nearest neighbor distributions. So given a set of data, if we ask at a particular search radius, where are all the query points that contribute to the value of the cumulative distribution function at that R? They will form these spheres around the data point. Some of them will intersect depending on the radius that you are interested in. So the value of the CDF is actually directly proportional to the volume contained in these spheres. Okay? So the CDF is simply proportional to the volume that you see on the figure. But now I can ask, at this particular R, how is my cumulative distribution function changing, or what is its first derivative, let's say. So that question can be reframed as asking, where are the query points that contribute to the change in the volume at that radius? And where are they? They are lying on the surfaces of these spheres. These are the outer intersections of these spheres. Again, I have a clear geometric interpretation of what the first derivative of the CDF at a particular point corresponds to. I can then ask, what does the second derivative correspond to? It turns out with some mathematics, you can show that the second derivative corresponds to these red areas, which are the angles of the intersections of spheres. Okay? There's a trivial piece which comes from the outer shape. Okay, so the second derivative of the CDF tells me the angles at which these spheres are intersecting. And finally, the third derivative of these cumulative distribution functions actually are directly related to what are called the Euler characteristic. So you have those unions of spheres. The third derivative of the CDF can be directly used to calculate the Euler characteristic of this complicated shape. So this was a neat sort of a conclusion. We were able to show that the first nearest neighbor CDF and its derivative have intuitive and beautiful geometrical or topological interpretations. And funnily enough, they are exactly equal to what are known as the Minkowski functionals in the literature. So the Minkowski functionals are the volume, the surface, the integral, mean curvature, and the Euler characteristic for a set of intersecting spheres. They don't have to be spheres, but anyway. However, all the Minkowski connections are to the 1NN CDF. You can give geometrical interpretations to the higher order CDFs as well. And the information in the higher KNN CDFs is beyond the traditional Minkowski functionals. So now we have tied it in, neatly both from the algebraic perspective of the endpoint functions and the geometrical or the Minkowski functional picture. So is that all that we can do with these statistics? The answer is no. We can also generalize these statistics to take into account cross correlations. I'll go over this a little more quickly because I have 5 more minutes. But what we have been able to do is generalize what I had shown you about the auto clustering of a set of points to talk about cross correlations. And again, in the cross correlations, we were able to write down the generating function in a closed form, and again show that these are related to terms that are integrals of the 2-point correlation function. But now since there are 2 types of data, one is red and one is blue, let's say, this is the integral over all configurations of 2 red points, 1 red, 1 blue, 2 blues. Then there is another term that are integrals over triangles of 3 reds, 1 blue, 2 red, 2 blue, 1 red, 3 blues, and so on. So if you measure cross correlations using this formalism, you are not only measuring what is called the Gaussian cross correlation between 2 data sets, but all possible correlations. So if you don't find correlations, this is called statistical independence. We also generalize the formalism to not only think about discrete data like red galaxies and blue galaxies, but cross correlations between one discrete data set and one continuous map. Okay, so for example, galaxies and 21 centimeter maps. What are some of the applications? So this is work led by my student Ishika, where she showed that if you're looking at cross correlations between, say, a chime-like experiment and a galaxy survey, if you use our cross correlation technique, which is on the right, compared to the 2-point function, sorry, my mistake. If you compare the signal to noise in the 2-point correlation function, which is here, the chi-square of the data lies within the null distribution. In other words, you get a very weak measurement of the cross correlation signal between chime and galaxies. If you use the nearest neighbor cross correlation method, this is the chi-square that you get. This is, I don't know, 10 sigma detection. Similarly, you can play around with the amount of time you integrate in chime, the noise, the foreground cleaning, and in every case, you get much stronger detection of the cross correlation signal if you use these nearest neighbor way of measuring correlations. Other applications. So this is work led by Kaustubh, who was my master student, and this goes back to what Shubhadeep was talking about. You might be interested in the dark siren method, but the dark siren method actually relies on measuring cross correlation between a galaxy sample and the BBH events. What we showed was that no matter what statistical significance threshold you set, suppose I want to detect at 5 sigma, the clustering signal, you will get there with far fewer events if you use the k nearest neighbor way of cross correlations compared to the 2-point that most people are using right now. Similarly, you might be interested in cross correlating high energy neutrino sources in IceCube with a galaxy sample, because we don't know exactly what sorts of galaxies or what sorts of events in these galaxies lead to these high energy neutrino emissions. Again, you would need far fewer sources to get a measurement of the cross correlation. So basically it's taking, cross correlations between things that look like this and things that look like that. Okay. Before I wrap up, you can also take the actual map. So this is the same data represented on the left and the right, except on the right, for every pixel, I have simply colored it by the distance to the nearest neighbor. Okay. And you can clearly see a nice pattern. This is actually the Voronoi tessellation of this picture. What I am doing with Othrideb, who was a postdoc at IUCAA and has now moved to Groningen, is to see if with machine learning, we can extract even more information out of this raw image compared to the information that we already capture in the distribution functions. Okay. We have some preliminary results, but I will not waste your time here. We can discuss this over coffee if you are interested. So let me summarize. So the k nearest neighbor measurements offer a new way of measuring cosmological clustering of nonlinear fields, both auto and cross correlations, and both continuous and discrete data. These are computationally extremely cheap. These scale just like the 2-point correlation function, yet they are sensitive to all endpoint functions in the data. There are analytic connections to higher order statistics, higher order endpoint functions. There are also really nice connections, geometric connections to the Minkowski functionals and other topological quantities. I didn't talk about it, but these nearest neighbor distributions can actually be well modeled on mildly nonlinear scales using this thing called the hybrid Lagrangian bias approach. On small scales, we have modeled it using an HOD framework. So we've also worked on the modeling part. If you're interested, we can talk about it. In the last couple of minutes, I want to show you our new website. So all my students got together, put together all of our code. And now if you're interested in these statistics and using them, you can simply go to this new website. It has example data sets, calculations, how to use it, and everything put together. So let me just see if it works. So this is our website. It's called KNNPy. It links to the actual GitHub repo where the codes are. There are also installation and user guides. There's also a list of all papers that we have put together on this. So if you're interested in what sorts of science questions you can address with this, take a look. And yeah, I just encourage you to download it and play around with it and see if you find anything interesting. And with that, I will stop and take questions.
Thank you for very nice talk. So how do you propagate the observational systematics into when you calculate KNNC, for example, masking or magnitude cuts and other things?
Very good. So masking, for example, we take into account by using a set of randoms. Usually all these surveys will have a set of randoms, and we look for the signal over and above what we get by throwing the query points with the mask included.
But then you will also have the interpretation of the first derivative a bit arbitrary near the masks.
Absolutely, yeah. That is absolutely true. So we often have to use a cutout region slightly larger than the mask to make sure that everything is robust.
Thank you.
Yeah, very nice work. So you talked about the link to the Minkowski functionals, and you made a statement that these are they can get more information out compared to Minkowski functionals. So how does that happen?
Yeah, so suppose you focus on a certain range of scales, right? Now, at the lowest R min, for example, some of those spheres have already intersected, let's say. So your Minkowski functionals actually start evaluating from that point on. So it doesn't have information of what has intersected before your R min of your analysis. But the higher end KNN CDFs actually can see the, let me see, might be here. So you can see that the higher KNN CDFs at a particular R are sensitive to what has intersected already. So that is how we get more information.
Okay. Then you stopped at the third derivative when you are making this. Can you not go higher derivative? Is there more information?
No, it stops there. We couldn't find a natural interpretation of higher derivatives actually. But you can also show that if you are in 3 dimensions, every intersection new intersection that you have, all the information is captured within the first 3 derivatives. So just like there cannot be more than 4 Minkowski functionals in 3D, we seem to have a similar sort of interpretation here.
Okay, thanks.
So just following on the Prakash question, so how do you deal with the foreground contaminations?
Yeah, so in the study with Ishika, what we did, Ishika and Simon and so on, what we did was the easiest way is to cut on K parallel. So we threw out the wedge.
Okay.
But as one of the talks mentioned in the morning, we could also try to model it slightly better. That is to be seen. We haven't really gone into details.
Okay, thank you.